Good afternoon, everybody. It's a delight to be here to address members of our fraternity, our community, and I'm particularly delighted to see so many young minds here. It gives me strength, and sometimes I feel that there is nothing better than to be a student, particularly in my own university. So I welcome everybody, and I appreciate this opportunity to speak on a subject that has been very dear to me, and I refer to the title, Infinity and the Art of Counting. Of course, I'm often asked, what does infinity mean? And you know, it's not an easy thing to grasp. Mathematicians look at it from a specific viewpoint. Philosophers look at it in overlapping ways, but even differently. The common person has his or her own conception of infinity. But when you become Vice Chancellor, then there's a new dimension. You know, when you sit in the sessions of the Academic Council, they extend up to infinity. You see. So then you begin to really understand infinity. Tell you about is really one of the most profound ideas and theories that any man of science or ideas has ever put forth in the realm of knowledge. And these ideas stem essentially from the mind of one man, whom I will name presently. And the simplicity of the ideas is such that any school child beyond the 8th or 9th grade can understand. But the depth, the elegance, the profundity of the ideas are such that they have brought about a revolution in mathematics. And I want to emphasize right at the beginning of my talk, especially to the young minds here, that it is in simplicity that beauty lies, that depth lies, that greatness lies. You look at the life of Mahatma Gandhi, he lived it so simply, so transparently. That is why he touched the hearts of millions and millions. And that applies to science as well, and mathematics particularly. So I will try and demonstrate that here. And what I speak of in the next 45 minutes or so is really what is called in mathematics the theory of sets, set theory. And it sprang from the mind of one man. His name is George Cantor. Cantor was a German mathematician who died in the last century, was born in the 19th century, who overlapped 2 centuries. This is George Cantor, and many may not even have heard of Cantor. But as I will explain, and I'm sure I will be able to convince you, it was Cantor's ideas that have really brought about a revolution in mathematics at a fundamental level. So what is it that I want to tell you about set theory? And you will, as I said, have to be a little patient with me, as I do not intend to be technical, but some simple illustrations will be in order, and I want to tell you what a set is. So let's see. I hope this goes well now. So I'm trying to tell you what a set is, and it's a very simple concept. You know, I'm not going to define it. I want to illustrate it by examples. That's the best way to do mathematics, to look at examples which illustrate a concept. I could speak of the set of students of the University of Delhi inside this hall. That's perfectly well defined. Everybody who's enrolled in some official program of the University of Delhi as a student is therefore a member of this set. I could talk of the set of ladies in this room, all females in this room. That's another well-defined set. I could talk of the set of all fans in this room. That's perfectly well defined, and you can tell who the members of this set are, the fans in this room. You know what a fan is. I could talk of the set of chairs in this room. Well defined again. You know what a chair is, and you can look at all the elements or members of this set, the chairs here. So that's how sets go. And I'll give you one or two other simple illustrations. So sets are generally labeled. I hope you can see that symbol here, the uppercase letter A. So sets are generally labeled by symbols which come from the English alphabet generally. And here's how mathematicians denote sets. So I could talk of the set of numbers 1, 2, and 3. This is a set. It has 3 members. The number 1, the number 2, the number 3. These are members of this set. The set is denoted by the symbol A. So A is a well-defined collection of the numbers 1, 2, 3. I could have another set, let's call it B. And that could be the letter X from the English alphabet and the number 1. A set of 2 members, X and 1. That's also a set. And everything inside the set. So for the set A, 1 is a member of A, 2 is a member of A, 3 is a member of A, and A has no other members. Similarly, for the set B, X is a member of B, 1 is a member of B, and B has no other members. I can talk of subsets of a set. These are simple concepts. So a subset is a set by itself, and it has as its members of a larger set. So a subset of A, I will illustrate, could be the set C, which consists of 1 and 2. So you notice that C has 2 members, 1 and 2, and they are both also members of A. So we say C is a subset of A. That's as simple as it is, a subset. And we look at these sets and we try and understand some things that will lead us to infinity in various ways. The theory of sets, as I told you, was propounded by Cantor. And there's one other thing I want to tell you. If you look at the history of ideas, not just in mathematics, you will always find that there is a series, a timeline, a sequence of events, happenings, thoughts that eventually lead one or a small group of people to then create a theory, a body of ideas that gets universal recognition. There are only 2 exceptions to my mind, 2 outstanding exceptions. There may be others. Einstein's general theory of relativity. I don't think even Einstein could explain exactly what led him to that. It is certainly clear that no one else had said a word about it. And the other idea that I can think of is the theory of sets by Cantor. Cantor conceived of this theory entirely by himself. There was no one before him who was thinking of similar lines which led Cantor to build upon that. Outside of that, I don't see examples. When Newton discovered so many things, he himself said that if I have been able to see farther than others, it is because I stood on the shoulders of giants. He was building on work that had gone before him. He was consulting, talking, reading ideas of others as well. This is not to take away the greatness of Newton, not at all. He was one of the greatest minds that ever lived. But I want to tell you that Cantor and Einstein stand out in this sense. And I choose to speak on Cantor today. So we talk of sets, And I want to tell you something now about numbers. I also want to tell you a little bit about numbers. That's really all the maths that we're going to discuss. So what do we understand by numbers? You know, all of us in this hall, I'm very sure, are fully acquainted with numbers which are called counting numbers. 1, 2, 3, 4, 5, and so on. And let me just write them for good measure. Doesn't write. One, 2, 3, 4, and so on. These are the counting numbers. See? How do we understand them? What do we mean by a counting number? What do we mean by these numbers? Look, you must only think of them as symbols that represent a certain abstraction. And I'll tell you what I mean. And let me just try and guess how primitive man dealt with the method of counting. And that's where I think the germs of Cantor's ideas lie. So I am trying to guess here that if there was some sort of primitive tribal person somewhere, and I don't mean tribal in derogatory sense, but maybe who did not have the sophistication of mathematics as we know it today, and suppose he had a herd of cattle with him, and the herd would go out to graze every day, and they would return in the evening, and the man needed to keep count of the herd. But he didn't know counting. He didn't know numbers. He wouldn't be able to enumerate on his fingertips like that. What do you think he would have done? And here's my guess. So he would collect a bunch of pebbles with him. And for each member of this herd that left his abode, he would plant a pebble somewhere together. So he would match against each member of this herd of cattle a pebble and keep collecting the pebbles together, and he would hold them with him, keep them somewhere. When the cattle returned, as I said, he doesn't know how to count. All he does is he matches again. He pairs the pebbles against the cattle one by one. If there are more pebbles than the cattle, then he knows that some cattle have been lost. And if he sees there are more cattle than the pebbles, then obviously somebody else's cattle has come over to his doorway. But that's how he kept count without knowing what 1 means, 2 means, 3 means, and so on. As time went by and thinking evolved and got more sophisticated, people began to think and they began to give symbols. That's how ideas began in counting. So if you had just one cattle, one pebble, you just denoted it by a symbol, which we do these days by this symbol 1 here. It's just a symbol. If you had 1 and 1 more, then you denoted it by another symbol 2. That's 2. And if you had 1 and 1 more and another, then you denoted it by 3. And now you just remember 3. Don't remember anything else. Automatically you think of this and you match this against 3 people, 3 cattle, 3 chairs, whatever. 1 for this chair, 1 for this chair, 1 for this chair. That's what you're doing. But now you don't do this. You don't keep the fingers with you. You don't keep the pebbles. You keep the symbol that represents 3 in your mind. That's how children are taught. So that's all there is to this mystery of these symbols. So there is this business of pairing that is going on, and you abstract that idea by these symbols. So when I say I have 45 cattle, what I'm saying is somewhere I can pair this off with 45 pebbles or something else. But that's it, nothing more, nothing less. 1 and 1 more and 1 more, you keep doing this 45 times. So that's called pairing. There is a sophisticated mathematical word for that. It's called one-to-one correspondence. So look, what was I doing here with the cattle and the pebbles? I had the set of pebbles that this man has. It's a set, the set of pebbles that he has with him. And the set of cattle that he has, it's another set. And how does he count them? Well, he pairs them off. So 1 pebble against 1 cattle, 1 pebble against 1 cattle, and then you see how many cattle there are by just collecting the pebbles. That's called one-to-one correspondence between the pebbles and the cattle. And you only keep as many pebbles as there are cattle. So this is a proper correspondence. No pebbles are left over, no cattle left over. Exactly matching. That is the profound idea that we will use throughout this lecture and nothing more. So, I want you to think, there are other numbers. How do we look at them? How do we learn about them? If I assume that you have understood what 1, 2, 3 mean, by the way I explained it to you, here's a way of understanding other numbers. Please believe me, this is a straight line, even if it doesn't look like one, okay? And I mark off a single point on this line and I call it the origin, O, or you can even think of it as 0. And then I just look at distance or length on this line. It's up to me. I choose a certain point or distance from 0 as my unit length or length 1. Okay? That's 1 unit. You could also think of it as the number 1 or the pebble 1. Right now, that length is what I'm interested in. 1 unit, length 1. When I double this unit length, I mark it off with the point 2, and similarly for 3, 4, and so on. Now, that's really the numbers that I spoke to you about, the counting numbers. But we know of other numbers. How about the number 1/2, half? For us, and a nice way to figure these things out for the rest of this lecture, what I mean by half is exactly that length which when doubled gives me the length 1. So, as we all know, it will lie midway between 0 and 1. The length half or the fraction half. That's also a length. Now, I have used a length to denote the number half. That's all you should think of it as half, the length half for my unit length that I have fixed. Throughout this lecture, that will be my fixed standard unit length representing the number 1. Half is half that length, or that which doubled gives me the full length. What do you think 1/3 will be? That length which added to itself 2 more times, altogether thrice, will give me the unit length. So it will be somewhere here. So it will be somewhere here, 1/3. I don't know if you can see that. That's 1/3. And if I just add it 2 more times, I'll get the length 1 back. See? That's 1/3. And I keep doing this. See? What would the length 4/5 mean? What number is that? So I divide the unit length into 5 equal parts. And 4 of those parts taken together is the number 4/5. So you look at that length, the distance, 4/5, that will lie, sorry, I keep pressing some button here. So 4/5 would be somewhere here at this point. See that? That's 4/5. I'm just trying to get you to understand what I mean by fractions. So if I had a fraction like 3/2, what do I mean by that? Here's what I mean. This is my definition. It's really nothing but the length 1 plus the length half. That's all there is to it. Nothing more. That's how I define it. And you can think of any fraction of the kind p divided by q. That's what fractions are called. And you will know what I mean by that by looking at lengths over here. If p is less than q, all you're doing is dividing the unit length into q equal parts and collecting p of them together, and that's the length p by q. And that's how I understand the fractions. Now look, I want to ask you, what do you understand? How do I go to the next page? What? Oh, this arrow? Okay. Okay, so look, I now have all the counting numbers, and there's a standard symbol in mathematics for these counting numbers. It's denoted by this. Okay, this is the set of counting numbers. What are they? 1, 2, 3, okay, and so on. Now look, you can all see that this is not a finite set. What do I mean by that? If you start looking at these numbers and start collecting them, it's not going to end. This business of putting them together one by one is never going to end. But I don't know if that's the best way to define or understand what is an infinite set. So Cantor came up with a marvelous idea. He said, here's how I define a set that has an infinite number of elements. Here's how I define it. You could have your own intuitive way of understanding it, but Cantor gave a proper, rigorous mathematical way of defining a set which has an infinite number of elements. He said a set will be called to have an infinite number of elements if that set can be put into one-to-one correspondence with a proper subset of itself. Let me explain what I mean by that. So let's look at this set n, 1, 2, 3, so on all the way to infinity. Why do I say this is an infinite set? Simply because of the following thing. I look at a proper subset of this set. When I say a proper subset, it means every member of this set is a member of the first set, but there are some members of the first set which are not in here. So if you can see, 1 is in n, but it is not in the set below it. So this set is a proper subset. But now look, even though this is properly contained in the set above, I can put the two sets into one-to-one correspondence. How do I do that? I pair 1 with 2, 2 with 3, 3 with 4, 4 with 5, and so on. And you will see that nothing is left in the top set, nothing is left in the bottom set. This pairing works off perfectly with each other. Nothing is left here, nothing is left here. That allows me to say that the set n is an infinite set. I can put it into one-to-one correspondence with a proper subset. If you were to look at this finite set, 1, 2, 3. It's not an infinite set. Why? Take any proper subset. A proper subset must have elements from this set, but some must be left out. So think of any one proper subset. Let's look at 1 and 3. See, this is a proper subset. Can I put them into one-to-one correspondence? Can I do a pairing in which nothing is left out either here, above or below? It cannot happen. No matter how I try, something will get left out. I could try this, this gets left out. And therefore, this set, the set above 1, 2, 3, can never be put into this pairing with a proper subset of itself, and therefore it is a finite set. Now this is a perfect, rigorous mathematical way of putting down infinite sets and finite sets. And that's Cantor's genius. Once he put this down, he was able to work magic. And that's what I'm going to try and explain to you. So what did Cantor do? Well, he began to study infinite sets. And that's where the magic really begins to unfold. It is amazing how things happen in this context. So let me just come back to the counting set. Just look at that. 1, 2, 3, 4, and so on. Let's look at a proper subset of this. That this is all natural numbers or counting numbers. Let's look at all even numbers. So here are all the even numbers. 2, 4, 6, 8, 10, so on. This is a proper subset. Here's the symbol for this set. 2n is a proper subset of n. If I ask you which is the larger set, in one context you will say n is larger than 2n because n has more elements. But actually from Cantor's viewpoint, they have the same number of elements. They can be paired with each other. Suppose this below, what I had were pebbles here, and over here these were cattle, not 1, 2, 3, but cattle number 1, cattle second, cattle third. I can pair them off and nothing will be left above or below. Here's how I pair them off. I pair 1 with 2, 2 with 4, 3 with 6, 4 with 8, and so on. In this pairing, Nothing is left in the above set, nothing is left in the set below. So it's completely paired off. And then Cantor said, therefore, the two sets have the same size. So look, on the number line, if you look at this, I had 1, I had 2, I had 3, I had 4, 5, 6, and so on. For the first set, all the numbers were included. For the second set, only these numbers are included. But by Cantor's logic, the two have the same number of elements because I can pair them off in this business. As I showed you above here, at the top, this pairing here at the top. Now here's the mystery. So I do this with just numbers of this kind, the counting numbers? No, I could look at the fractions. So Cantor said, okay, let's look at these fractions, 1, 1 by 2, 1 is also a fraction, okay? 1 by 3, 2 by 3, and so on. If you look at all these fractions and if you try and understand them on the number line, suppose just between 0 and 1, God, there are all kinds of fractions. This could be 1 by 8, this could be 2 by 5, this could be 8 upon 9. All of these, this could be half, so many, and there are infinite number of them. You can see by understanding that this process never comes to an end. So there are infinite number of sets here, infinite number of numbers here between 0 and 1, the fractions. Now just think of the whole number line. Can you imagine how many fractions there are? There are fractions everywhere. You touch any point, almost certainly it will be a fraction. Not always, but almost certainly. It's going to be a fraction, 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 everywhere on the whole number line. They are dense in even mathematical terms or even visual terms. They are dense on the number line, whereas the counting numbers are not dense. They are spread discretely. But Cantor showed that the two have the same number of elements. Exactly. He paired off the fractions against the counting numbers. That created a huge ripple in mathematics because it's counterintuitive. If you look at all the fractions, as I just told you, they are completely spread densely on the number line. There are too many of them. Whereas the counting numbers happen at fixed intervals and they go on in such a staid fashion, sedate fashion. And yet Cantor showed that the two have the same number of elements. That was magical, but then it created some problems for Cantor. However, I'll come to the problems in a while, and you may think mathematics is a great discipline, it is so precise, so logical, and nobody can really counter you or argue with you because you're doing something rigorous. But mathematicians are also human, and they also make all kinds of mistakes. There are also jealousies. They're subject to all these weaknesses and failings of the human nature. And so they also create trouble. I don't know if this will hearten you or disappoint you, but that is a fact. And it happened with Cantor too. But let me quickly just move to one more point. So Cantor said that here's my symbol, my way of telling you what are the sets that can be paired with the counting numbers. So remember, this pairing is just one-to-one correspondence. Nothing gets left in one set or the other set. They're perfectly paired against each other. One against one. And he said any set that can be paired with the counting numbers will be said to have the same size as the size of the counting numbers. Perfectly natural. And he said, I represent that size by this symbol, LF naught. Okay? That's the symbol that tells me if I say this set of fractions has size LF naught, all I mean is that it can be put into one-to-one correspondence with the counting numbers. Then Cantor, began to ask. Remember I told you on the number line, you have the counting numbers, you have the fractions, and so on. But there are some other lengths which are neither fractions nor counting numbers. I can talk of a number called square root of 2. Don't worry what it means. But it is certainly a length somewhere here. represented by this symbol, it's a length. And you can prove that it can never be a fraction. So there are other kinds of lengths which are neither fraction. And Cantor proved, so did others, that such numbers which are not fraction lengths are also dense on the number line. The points which mark these lengths, if you look at those points, they will actually appear as a dense infinite collection, just like that, visually. Forget the mathematical meaning. And then he asked, what is the size of this set? Those lengths that cannot be put down as lengths of fractions. What is the size of, what is the collection of, the size of this collection of lengths? And he gave such a marvelous argument. It is what is called argument by contradiction. And he showed that this is larger than the size of the counting numbers. So remember, both are infinite sets. The counting numbers and these lengths which are not fractions. And then he showed that the lengths which are not fractions, if you collect that set, those numbers, it is infinite certainly, counting numbers are infinite, but this infinity is larger than that infinity. That is revolutionary. Cantor began to talk of orders of infinity, one infinity being less than another. You know, the lesser gods, जिसको देवगण कहते हैं, less than the supreme being. Something like that, a lesser god. They're both gods, but this God is greater. They're infinite, both of them. And he proved that through an ingenious argument. Can I see that slide X? Look, here's how Cantor looked at it. You know, the argument has nothing to do with what Cantor did, but I'm just going to show you what Cantor did in a different way. Suppose you take the two letters X and A. Just take two letters, X and A, and you arrange them in whatever order you like. So the first arrangement is X, A, X, X, A, and so on. The second arrangement is X, A, X, A, X, and God knows what. And the third is A, A, X, A. I leave the choice to you. But you look at all possible arrangements. I'm just trying to give you what Cantor said, how he showed that all the lengths which are not fraction, this infinite collection of numbers, is of an order of infinity larger than the infinity of counting numbers. So the argument that he gave is really ingenious. You just take two letters X and A, arrange them in all possible ways in an infinite sequence. So the first arrangement goes on as much as you like, or you could stop it at some point. Second goes on in any way you like, all possible. Now suppose that this arrangement, that's going to be infinity in number. So first arrangement, second, third, I mean, God knows how many. What Cantor showed was this infinite set of arrangements is going to be more than the counting numbers. And how did he prove that? It was remarkable. So what did he do? He said, suppose this infinite set of arrangements that you make, howsoever, all choices possible, if they were countable, that means if they could be put into one-to-one correspondence, you will end up with a problem. And here's how he proved it. So he said, look, I'm going to give you an arrangement that can never be in any listing that you put here. So here's what he did. He said, let me start with this arrangement. The first letter in the arrangement will be A if the first letter of the correspondence is X. The second letter will be X if the second letter of the second correspondence is A. The third letter will be A if the third letter of the third correspondence is X. So he wrote down another arrangement like this. And now this is also an arrangement, but is the entire listing, if that were countable, then you will find that it differs from every element of the listing. In the first listing, the first letters are different. In the second listing, the second letters are different. In the third listing, the third letters are different. So this listing is different from all other listings. And so he produced a new listing, no matter how many ways you had listed your listings here in all possible combinations. That stunned the world. They didn't accept it. People began to object to Cantor. Now people were beginning to get mad. They were hopping mad. What is he talking about? But you know, you couldn't find a flaw in his argument. There is nothing, there is no mathematics here. What mathematics have I talked about? Have I used the calculus? Have I used any algebra? Nothing. It is pure and simple pairing and a little bit of simple logic. But he's dealing with numbers, and people were dealing with numbers all the time in mathematics, and yet they hadn't understood that there are different orders of infinity. This is just about as technical as I'm going to get, nothing more than this. And Cantor began to make magical things. But you know, there was resentment growing against Cantor. Some of it was jealousy, some of it was misunderstanding. Some of it is, you know, when you're confronted with something new, and if you're not particularly used to handling new things, then you have no option but to get angry. And if these ideas are that profound, that earth-shaking, no one had thought of that. That infinity can have different sizes. One infinity can be larger than another infinity. So that began to shake people. And infinity is a tricky thing. You have to be really careful or you'll get your fingers burnt. And I'll give you one example. Can I show them Hilbert's Hotel? Where do I go? Okay, this is David Hilbert, one of the greatest mathematicians of the 20th century. And Hilbert produced an interesting insight into what kind of tricks infinity can play with you. So let me just show you what is called Hilbert's Hotel. This is a hotel which has an infinite number of rooms. There's the first room, there's the second room, the third room, the fourth room, and so on. And each of these rooms is occupied. So this is a hotel which has full occupancy. Now suppose a guest turns up. What do you think the hotel will tell them? That we have no rooms? Will the guest go back? No. You can still create room without throwing any guest out. And here's how you do it. All you do is, the hotel at the top is the one which has full occupancy. The manager tells every guest, please exit your room and move one room to the right. So they move. The first guest goes to the room in the second place. The second guest goes to the third room. The third guest goes to the fourth room. All the guests are still in their rooms because this goes on to infinity. But now you have a vacancy here, so you can accommodate the guest. So infinity can play all kinds of tricks on you. And the tricks can be even funnier. This was for just one guest. Suppose, for the sake of argument, an infinite number of guests now turn up. Infinite number of guests, and you're fully occupied. What do you think the manager will do? He can still accommodate them all. You know, all he has to do is tell the guest in room number 1 to go to room number 2. Tell the guest in room number 2 to go to the room number 4. Tell the guest in room number 3 to go to room number 6. What is he doing? Asking each person to go to double the number of the room in which he already is. So 1 goes to 2, 2 person goes to 4, 3 person goes to 6. Now look, there are vacancies here. Every alternate room is now vacant. And this goes on to infinity. So all these infinite number of guests can still be accommodated. So infinity is a very tricky thing. Remember, you are almost playing with God here, so you be careful. That's how it is. So it goes on this way. It's very, very tricky. But you know, I told you, people were getting upset with Cantor. Amongst the people who were getting upset, there was a German mathematician by the name of Kronecker, whom Cantor knew very well. They used to meet often. And Kronecker was very upset, and he began to attack Cantor's work. He said, this is all utter nonsense. He called this is witchcraft. And Kronecker was a very famous mathematician, one of the best of his day. And when someone like that attacks your work, it does have an effect. So people, mathematicians, began to get divided along two lines. Those who tried to accept what Cantor was doing, and those who objected to what Cantor was doing. Remember, Kronecker wasn't really coming up with any mathematical argument, but his reputation as a mathematician was so strong that when he said something like this, people began to think and take it seriously. They were getting upset. Kronecker says something, let's look at it carefully. Maybe he's right, maybe Cantor is wrong. Why does he talk of different orders of infinity? There is nothing like that. There's just one infinity. One infinity cannot be larger than another infinity. And I want to halt here for a minute from this sequence of events and tell you something else. You know, I said something at the beginning that Cantor's ideas came out of total thin air, blue, totally out of the blue, picked it out of a hat. But there's something that I misled you about. Cantor certainly didn't know this. But 300 years before Christ, in India, there were Jain mathematicians who were also looking at infinity in a mathematical, logical way. And the Jains had done marvelous work. It is still not fully understood. But Jain texts talk of different orders of infinity in the logical sense. The ideas and the words and terminology they use match a reasonable amount of what Cantor had to say. Of course, the contrast is this. They were doing it in India 300 years before Christ. Cantor was using the entire power of European mathematics that was at his command. There's this big difference. I say this only because I want the young to understand the true heritage we have in India. This richness, the power of our ideas, the richness of our ideas. And I don't want the young to lose themselves in this spirit that everything comes to us from this Eurocentric or Western viewpoint. It doesn't. It's in our bloods too, It's in our heritage. And I don't want you to sit back and gloat about it. But I do want you to take courage, to take heart, to take pride, and be propelled to do equally or greater things. That is why I mentioned this. And I thought it would be of interest to you. Cantor then went on to do other things. I just gave you one example of his magical arguments, which is so simple, but tells you there are different orders of infinity. So he then said that between the order of infinity of the counting numbers and the order of infinity of all the numbers which are not fractions, there cannot be any other order of infinity. Other orders of infinity will be greater than the order of those numbers which are not fractions. So between, oops, how do I go back to the blank slide? 32? Okay. So here's what Cantor said. You see, he said that I denote the order of infinity of the counting numbers by this, and I denote the order of infinity. Something's gone wrong. Did I switch something off? Sorry? Okay, thanks. And he said, I denote the order of infinity of the numbers that are not fractions by C. He said, of course, this order is larger than this order, and there is no infinity between the two. And he called it the continuum hypothesis. Why did he call it continuum? Because this set of all numbers on the number line is a continuum. That's what Cantor had said. And that between this continuum and the counting numbers, there is no other size of infinity. That was his conjecture. Actually, he said he believed it, and he said, I can prove it. But you know, by now the attacks had begun to be very vicious. And Cantor began to doubt his own work. He started getting depressed. He was actually despairing and becoming depressed. His letters indicate that. And then some tragic things began to happen. People began to discover paradoxes in set theory. This business of sets that Cantor was talking about led to contradictions. And I will speak to you about Russell's paradox. Maybe you know about it, maybe you don't. But in layperson's terms, non-technical, non-mathematical, non-logical, here is what Russell's paradox says. That suppose there is an island, completely isolated, in the ocean. And in that island, there are a bunch of males. Bad luck, nobody else, just males. And there is a barber amongst them, just one barber. And the barber shaves all who don't shave by themselves. You get my point? So you have this luxury of the barber shaving you if you don't shave by yourself. Now the question is, who shaves the barber? The rule is this. It's a simple rule. You get shaved by the barber only if you don't shave yourself. But if the barber were to shave himself, then the rule applies. Then the barber cannot shave himself. And if the barber doesn't shave himself, then he has to be shaved by the barber. You see that? That's a paradox. You cannot resolve it. Actually, this paradox can be translated into the language of sets. And you know, things began to get worse for Cantor. Probably the greatest living mathematician of that time, Poincaré, a French mathematician. Poincaré made a comment which is, at this point when we look back on history, it is almost unforgivable. And remember, I speak with great respect for Poincaré. He wasn't a disease that 20th century mathematics will have recovered from. And you know, for Cantor, this must have been heartbreaking. And I wish Poincaré had been a little more thoughtful, but you know, we forgive him. There may have been reasons. He must have said it for honest purposes. But it devastated Cantor. However, you know, there is always a knight in shining armor. And that knight happened to be David Hilbert. He came forward, and Hilbert began to resurrect Cantor's set theory. He understood its importance. He understood that it strikes at the very fundamentals of mathematics. These are answers that cannot be handled easily. You're dealing with infinity. You're trying to count infinity. This art of counting that Cantor invented is where we need to look at carefully. And under Hilbert's influence, a school of mathematics in Europe, particularly Germany, particularly Göttingen, where Hilbert was, where his followers were, they began to look at set theory in a proper way. And they began to try and make it axiomatic, make it precise and logical. So they set down certain axioms that are held as evident truths. And from these axioms, everything else in set theory should be derived. That was their purpose. Now, you have already encountered this in school when you handle Euclidean geometry. You know, the whole of Euclidean geometry has 5 axioms that you assume as self-evident truths. The 5th axiom, the 5th postulate of Euclid says that if you have a straight line and if you have a point outside the straight line, then one and only one straight line can pass through that point which is parallel to the other line. One and only. That's self-evident. Or we think so. We think it is self-evident. In exactly the same fashion, Zermelo and Frankel, 2 of Hilbert's disciples, decided to lay down certain self-evident truths of set theory from which the rest could be derived. And they thought that if we limit this business of handling sets which are too large, then maybe these paradoxes can be done away with. So Zermelo-Frankel axiomatic set theory began to gain acceptance all over the world. But Cantor's continuum hypothesis that there is no infinity between the counting numbers and all numbers that are not fractions, that was still unresolved. And people thought now that we have this axiomatic Zermelo-Frankel set theory, we can resolve the matter. But nobody really could come up with anything. And then they came across this supreme logician from Austria called Kurt Gödel. And Gödel produced a remarkable argument which showed something very nice. He said, well, what we don't know much about the continuum hypothesis. It may be true, it may be false. Let's suppose it is true. Let us assume it as an axiom. Let us assume it as an axiom. So let us take all the axioms of Zermelo-Frankel that were already there, add one more axiom. Then he said, suppose you arrive at some stupid contradictory statement that doesn't make sense. After using all these axioms that Zermelo-Frankel theory had and the axiom that Cantor's statement said, the continuum hypothesis is true. You use that as an axiom. If you come to a contradiction, then he said the contradiction does not come from the continuum hypothesis. It is coming from the other axioms of Zermelo-Frankel. So he showed something remarkable. You can use it as an axiom. Your axiomatic system will not lead to trouble. because of this other additional axiom. If at all there is trouble, it will come from the other axioms. That was interesting. But it still doesn't tell you whether the continuum hypothesis is true or not. And then following Kurt Gödel in the 60s, an American mathematician by the name of Paul Cohen got into the act. And he said, okay, let's assume all the axioms of Zermelo-Fraenkel. Let's assume continuum hypothesis is not true. That means there is another order of infinity between the counting numbers and the numbers that are not fractions. And let's take that as an axiom also. And now suppose, he said, you come into some trouble, some contradiction. Then he said that contradiction cannot come from the negation of the continuum hypothesis being used as an axiom. It is again coming from Zermelo-Fraenkel axioms. Now that was path-breaking. What does it show? It shows that the continuum hypothesis is independent of the axioms of set theory. It is neither true nor false. Na satya hai, na asatya hai. You know, in the Bhagavad Gita, and I don't endorse any religion, please don't misunderstand me, but I cannot help noticing this. When Krishna talks of what he is within this realm of nature that Arjun knows, he says, na main satya hu, na asatya hu. And I've heard people say who understand philosophy in a limited way, how can that be? Either something is true or it is false. And I always point them to this continuum hypothesis. It is perfectly logical as a statement. It exists within this system. It is derived from the words and terminology and the matter around you in set theory. But it is independent of the axioms of set theory. You can neither prove it nor disprove it. And you know, this goes on. It doesn't end here. So what happens to the continuum hypothesis? How do you handle it? So there are efforts going on in many ways, some making some sense, some not making any sense at all, to recalibrate and add or subtract some axioms of Zermelo-Fraenkel so that you can bring continuum hypothesis back into the ambit either as true or false. Many mathematicians believe this task will succeed and it will be shown to be false. Many believe that it will be shown to be true. But I believe they will probably not be able to do anything. And I'll tell you why. I mentioned Kurt Gödel to you. His work is directly derived from Cantor's continuum hypothesis. So it is Cantor's ideas that shook mathematics. They began to look at the foundations of mathematics. And Gödel showed something remarkable. He said, no matter what system of axioms you have, provided it satisfies some simple, reasonable things. I don't want to define what is reasonable, but assume that it is easily understandable. Then what did Gödel show? He said, if I have a system of axioms which is reasonable, there will always be statements derived in the system from perfectly logical ways as a statement, but they will be neither true nor false in that system. It will always happen. Not only that, he said something else. So you begin to worry. I may assume a bunch of axioms and then I build a whole theory like I did with Euclidean geometry. But then, how do I know that these axioms are not mutually contradictory? At some stage, all these so-called self-evident truths may end up in trouble somewhere. And Gödel showed that you can never establish the consistency of your axioms by staying within the axiomatic system. You will never know. So, you know, all these things, they shake you up. We mathematicians build all these axiomatic systems. We do mathematics, we fly planes, we have the internet, we have computers, all based on maths. I don't know, maybe something may happen. I want the young minds to think about this. I want to stimulate the minds about this. All these problems are unanswered. Of course, problems will always remain. This is the world of God around us. Hari Ananta, Hari Katha Ananta. It will never end. We may fool ourselves that now we have Einstein's theory. They said the same when Newton came, that everything that was worth knowing was already known. But Einstein came along and he showed that's not true. And I'm sure one day they will build on that. And the world of mathematics will also proceed like that. So my friends, all I was trying to say was this art of counting infinity, much as it is logical, much as it is precise, also leads you into great and profound ideas. And it starts with such simple things. So I urge you to think of the simple things. Keep the idea simple, but be bold like Cantor was.